Welcome to G Fun Facts Online. Today, we're journeying to the edge of planetary science to uncover a new class of world emerging from the cosmic shadows. These errant super-Earths, or mini-Neptunes. Astronomers are calling them super-Venuses, and they are forcing us to rethink the very nature of planets. Imagine our solar system's hellish twin, Venus, but scaled up, more massive, and amplified to an unimaginable extreme. Thanks to new observations, we're peeling back the first layers of these scorching, mysterious worlds. For decades, our concept of planets was shaped by our own solar system. We had rocky worlds like Earth and Mars, and gas giants like Jupiter and Saturn. But as our telescopes grew more powerful, the floodgates opened. We started finding a menagerie of alien worlds, and one type appeared over and over. Planets larger than Earth, but smaller than Neptune, a size not found in our cosmic neighborhood. Scientists debated what these intermediate planets were. Were they super-Earths, just bigger versions of our world, maybe with thin atmospheres? Or were they mini-Neptunes, with thick, gassy envelopes and perhaps vast oceans? The lines were blurry, and thick clouds often hid their secrets, making it nearly impossible to know for sure. But then came the James Webb Space Telescope, or JWST. It has given us an unprecedented window into the atmospheres of these distant worlds. One of its most fascinating targets is a planet called GJ 1214b, just 48 light-years away. Discovered in 2009, this planet is about 2.7 times the size of Earth and 8.2 times more massive. For years, it was thought to be a potential water world. But for over a decade, its true nature was hidden behind a stubborn, impenetrable haze. JWST finally lifted that veil, and what it found was far more extreme than anyone imagined. Instead of a water-rich or hydrogen-filled atmosphere, the data showed the signature of a world choked by dense carbon dioxide. This startling discovery led scientists to propose a new planetary classification, the super-Venus. So what exactly is a super-Venus? The term paints a vivid picture. These aren't just slightly larger Venuses. They represent a class of planet where the Venusian inferno is amplified to a planetary scale. While our Venus is a terrestrial planet with a thick, toxic atmosphere, a super-Venus is a more massive world that has ended up in an even more extreme, runaway greenhouse state. The key characteristics are starting to become clear. First, their size and mass place them squarely in that gap between super-Earths and mini-Neptunes. Second, and this is crucial, they have a thick atmosphere dominated by carbon dioxide, not the hydrogen and helium you'd expect on a mini-Neptune. This is what's called a secondary atmosphere, one that forms after the planet's original primordial one is lost. Third, the temperatures and pressures are extreme. Thanks to the intense greenhouse effect from all that CO2, surface temperatures are predicted to be even hotter than on Venus, possibly exceeding 800 degrees Fahrenheit or 1,000 degrees Celsius. The atmospheric pressure could be hundreds of times that of Earth's. Fourth, just like Venus is perpetually shrouded in clouds of sulfuric acid, super-Venuses have thick layers of haze that obscure their lower atmospheres. Finally, their atmospheres are described as metal-rich. In astronomy, metals means any element heavier than hydrogen and helium. So, a metal-rich atmosphere has a high proportion of elements like carbon and oxygen. In the deepest, hottest layers, it could even contain vaporized rock and metals. The story of GJ 1214b is what brought this new class into focus. Before JWST, the best guess was a mini-Neptune or a water world. But the new data showed a small but clear signal of carbon dioxide, with no significant evidence of water or hydrogen. This forced a major reevaluation, leading to the idea that we're looking at our first real super-Venus. How does a planet become such a hellish world? The answer is a complex story of formation, evolution, and a planet's relationship with its star. One major factor is the intense radiation from the host star. For planets orbiting close to their stars, especially the small, active stars known as M-dwarfs, this radiation can be powerful enough to strip away the planet's original, primary atmosphere of hydrogen and helium. This process is called atmospheric escape. Once the primary atmosphere is gone, a new, secondary atmosphere can form through massive, sustained volcanic activity from the planet's interior. This is where the path to a supervenus diverges from that of a habitable world like Earth. On our planet, liquid water oceans were crucial. They dissolved carbon dioxide from the atmosphere, which eventually got locked away in carbonate rocks. This acted as a planetary thermostat. But on a hotter, drier world, or one that lost its water to space, this regulatory mechanism is missing. Instead, volcanoes can pump vast quantities of CO2 and other greenhouse gases into the air for millions of years. With no way to remove it, the CO2 builds up, trapping more and more heat. This drives the surface temperature higher, which can create a magma ocean. This molten surface then releases even more trapped gases into the atmosphere, creating a runaway feedback loop. We have compelling evidence for this scenario from another exoplanet, 55 Cancri e. This super-Earth is so hot its surface is likely a molten ocean of lava. And JWST has found it has a substantial atmosphere, rich in carbon dioxide or carbon monoxide, which is likely being constantly replenished by outgassing from that magma ocean below. So what would it be like to descend through the atmosphere of a supervenus? At the heart of it all is the runaway greenhouse effect, but on a scale far grander than on Venus. The greater mass of a supervenus means it has stronger gravity, allowing it to hold onto a much thicker atmosphere. As the planet heats up, any surface water would boil away, adding water vapor, a powerful greenhouse gas, to the air. This drives temperatures even higher, a vicious cycle that ends only when all the water is gone, with much of it lost to space. Recent climate models show that this transition can be surprisingly abrupt. A small increase in solar radiation can be enough to push a planet over the edge, turning it from a potentially temperate world into a sterile, scorching inferno. One of the most puzzling features of these worlds is the thick, impenetrable haze in their upper atmospheres. This haze is what hid GJ1214b from us for so long. Surprisingly, JWST found that this haze is highly reflective. Many scientists expected it to be a dark, sooty substance. Its exact composition is a mystery, but it might be a type of photochemical smog, similar to what's on Saturn's moon Titan, but formed under much hotter conditions. Laboratory experiments are trying to replicate these conditions to figure out what chemical reactions could produce it. Even more exotic is the idea that the lower atmospheres of supervenuses could contain vaporized metals. On some ultra-hot exoplanets, temperatures are so extreme that even rocks and metals turn into gas. While GJ1214b isn't quite that hot, it's still hot enough that some of the more volatile metals could be vaporized in its lower layers, contributing to that overall metal-rich composition. The atmospheres of supervenuses are also likely incredibly dynamic. Venus itself is famous for its super-rotating atmosphere, which whips around the planet in just 4 Earth days, much faster than the planet's own slow 243-day rotation. On a tidally locked supervenus, where one side permanently faces its star, the temperature difference between the day and night sides would be extreme. This would drive powerful winds, thousands of kilometers per hour, as hot air on the day side rises and flows toward the cooler night side. This could create a form of superrotation even more extreme than what we see on Venus. GJ1214b might be the poster child for this new class, but it's not alone. As our observations improve, we're finding other candidates. We already mentioned 55 Cancri e, the lava world with a secondary atmosphere. There's also Kepler 69c, which orbits a sun-like star and receives a similar amount of radiation as Venus, leading to speculation that it too could be a supervenus. The case of another planet, TOI 1685b, shows how challenging this research is. Early observations suggested it might be a water world, but more recent studies with JWST indicate it's likely just a bare, dark rock. Our understanding can change rapidly with new data. Studying these atmospheres is one of the greatest challenges in astronomy. Trying to detect chemical signatures in the atmosphere of GJ 1214b was described by one astronomer as being given 2 copies of War and Peace and being asked to find the one sentence that has been changed. The primary method we use is called transit spectroscopy. When a planet passes in front of its star, some of the starlight filters through its atmosphere. By analyzing the spectrum of that light, we can see the absorption signatures of different molecules, revealing the atmospheric composition. The James Webb Space Telescope has been the key, with its powerful infrared instruments that can see through the haze that blocks visible light. Combined with high-resolution spectrographs on ground-based telescopes and complex computer models, we can begin to piece together the properties of these alien atmospheres. The study of supervenuses is just beginning, but the future is exciting. JWST will continue to be a primary tool, but astronomers are already designing the next generation of great observatories. Concepts like the Large UV Optical/IR Surveyor, or LUVOIR, and the Habitable Exoplanet Observatory, or HABEX, aim to directly image Earth-like planets and study their atmospheres in unprecedented detail. While their main goal is the search for life, they will be invaluable for studying the full diversity of exoplanets, including supervenuses. On the ground, the giant Magellan Telescope, now under construction, will have a resolving power 10 times greater than the Hubble Space Telescope, allowing it to probe these atmospheres with incredible precision. With these new tools, astronomers hope to answer the big questions. How common are supervenuses? What is the full range of their atmospheric compositions? What precise processes lead to their formation? And what can they teach us about the early history of our own solar system and the fork in the road that sent Earth and Venus on such dramatically different paths? The discovery of the supervenus class is a powerful reminder of the incredible diversity of worlds in our galaxy. These hellish, scorching planets might not be habitable, but they are fascinating natural laboratories. They help us understand the grand processes that shape planets and their atmospheres. As we continue to explore the cosmos with ever more powerful tools, the secrets of these exotic new worlds will continue to unfold, pushing the boundaries of our knowledge and inspiring new questions about our place in the universe. Thanks for listening to G Fun Facts Online.